Hey everybody, today I'm back to talk about laser cutting performance. I've done a few videos on how to focus the laser properly to get the best, smallest dot for engraving and things like that. But I've never really spent much time characterizing what's the optimum height for getting the best cutting performance. So when you're cutting different materials like this thin material, should the focus point be right on the top or in the middle of it? And then when you're, say, cutting 3 passes through a thick piece of cherry, where should the focal point be for the best performance there? And should it be at a different point for each pass that you make? So the reason all this started was a couple weeks ago I posted a video what this new XT8 laser from Opt Lasers could cut. It's a 45 watt laser. It's got a longer focal length. It's a really nice laser. And I published it, and the CEO sent me an email and said, hey, I think you should have got better results than that. We get better results in our testing here. And I said, okay. And then he said, well, I'm going to send you a new laser to test out because we want to make sure that the original one I had was kind of I won't say prototype, but it was a first production run, and they made some changes since to optimize a few things. So they sent me that to test out. And there were some differences, and I'm going to do a separate video on ultimately what the production model of this laser will do. But in this video, I just want to talk about how do we find out what the best method for cutting is. Should I cut fast? Should I cut slow? Where is the focal height supposed to be? So I did a bunch of cutting. I'll show you. I spent a couple days here just cutting stuff in my shop here, and a couple things kind of surprised me. When I started this first, I went looking online, and there's very little information out there. There's a lot of information how to focus and get the best dot for engraving, but not for cutting. A lot of people talk about, well, lower it for each pass, but they don't say how much or anything, or how to find out what the best way is. I ran across a video by a guy named Russ. He has a video channel called Sarber Media. He's almost got 400 videos on lasers. Very, very informative. The guy's retired. He just goes through and meticulously characterizes and digs into things and tries to understand them. And he's gone, it's a very interesting channel. I've spent a lot of hours watching it. But he's gone through CO2 lasers, and then he did some fiber laser stuff, and now in his last, 20 or so videos, he's been covering a blue, I think it's he had a 1 diode and then a 2 diode laser, but he had a really interesting video that he just released a couple days before I started looking for this, where he was doing some characterization on cutting depth. And so I watched that, and that gave me a few ideas, and it also kind of gave some explanation of a couple of weird things that I've noticed, where the angle of the cone of the focal of the beam being focused didn't really line up to my expectations about cutting, and I think some of his explanations made sense. So I'm going to go over that on the grease board first to explain that, and then I'm going to go over some of the cutting results, and then I'll post the table and stuff. But I based on what Russ had done, I made some modifications, and I came up with a pretty good way to characterize this. So the numbers I'm going to publish are probably going to be accurate for this model of laser, but the methodology that I'm going to present you can use for any laser. You just have to go through the steps that I did and find out the best position to put your laser in Z height wise to get your fastest and cleanest cutting performance. So I got a pretty big pile of material that I went through. Everything from composite materials, MDF, various plywoods. My thickest material was some polyene that's about 0.9 inches thick, so almost an inch thick, and I could cut all the way through with this laser. I even tried some foam, cardboard, different plastics. So I've got a whole table that I'll show in the end, but the methodology that I used is very much the same. So what I did was I wrote a G-code file that basically starts off the edge of a piece of wood and cuts into it. So it's basically making these lines from outside to inside. And the first line starts at z equals 0. So z0 is where the smallest dot or the tiniest focal point is right at the surface of the material. And then I go down from there. So minus 25 thousandths, which for those of you who aren't in the US, that's about a half a millimeter. So I go down 25 thousandths at a time to 300. So 200 is right at 5 millimeters. So it's about 7.5 millimeters is the lowest I went between there. And then I ran constant speed and 100% power. So the speed I picked was 15 inches per minute. The reason I did that was because for my previous cutting tests in organic, mostly wood-like materials, that's a good cutting speed where it seemed to give a pretty clean cut without severe burning. If you don't go fast enough, you'll get some really severe kind of fringe burning, and I'll explain that and show what that looks like in a minute. But basically, I'm looking to see where I get the deepest depth of cut. So I run this thing, and I do, by the way, I do it both in the X and the Y direction. So when I put this down, I have to turn the workpiece because they're obviously on the same edge here, even though these axes cut perpendicular to each other. The reason I did that is because I wanted to know, I was also curious if, because a diode laser has a fairly asymmetrical beam quality, it doesn't, typically they will cut much more in one axis than the other. So where I started out was with a material I knew I couldn't cut through in one pass, because I want to start out with the first pass, finding out what's the best focal point for that. And then once I have that, I'll move on for the second and third pass to see if that's different. So here, looking at these lines on my machine, the deepest ones were generally between 150 and 200 thousandths lower than my focal point. So, and not exactly, but what I was trying to do is find the sweet spot, because I don't want a different number for every material and every cutting condition. What I'd really like is kind of the sweet spot where I don't have to change the parameters a lot. So I cut tons of material. I just cut all kinds of different materials, different thicknesses and everything. First of all, to find out, is the X and Y axis the same? Is it different for different materials, etc.? So what I did find out is that I get a very consistent, thickest or deepest cut, generally between, like I said, 150 to 200, maybe 225 thousandths lower than the surface. You can kind of see, for example, here, where these four are about the same depth. And on this one, you can see the same thing. These four are about the same depth. So when you're too high, you don't get down as far. When you're too low, what happens is you start to drop down, and some of the fringe burning kicks in. So generally you can see how the line is thinner here, and then it starts to get really fat, and that's because you're dropping down so far that the top of the beam is widening out, and that starts to kind of mess up the looks. You don't have a clean of a cut, but you also don't get as deep typically. On this one here, it almost looks like it's just about as deep, but you can see clearly, for example, on this one, the last one is not as deep. And generally, the last couple were not as deep on most of the materials. So that's the test file that I was running multiple times. So what I did was, after looking at all the materials and all the tests on the first pass, I concluded that minus 200 was the best thing, or best depth. So then what I did is I changed the tool path. So the first thing it did was it cut all of these lines at the same distance on the first pass. So I added a first pass in there, so they all cut at minus 200 all the way down. And then the second pass followed the original series of depths. And so my question was, okay, I know what gives me the deepest cut on the first pass. Now, does that same focus point give me the deepest cut on the second pass, or is that a different depth? Maybe it's got to be a little bit lower for each pass. Well, what I found out again was that on the second pass, minus 200 was again on average the best depth, which is really cool. So then I did a third one the same way, where I had 2 passes at minus 200 and then did the third pass with progressively deeper, and lo and behold, the third pass also was optimal at minus 200, which is great. So now you can, whether you're doing one or multiple passes, the same value can be used. So then my question was, on thin materials that I can cut in one pass that are significantly less than that 200,000, so say this MDF is an 1/8 inch. All of these materials here, 1/4 inch plywood, 1/4 inch plastic, cardboard, all those things, should those also be cut at minus 200? And the answer is no. So what I did with those is I started at 0, and then I tried it with the focal point right in the middle. So in this case, I would go to minus 65 thousandths, because this is 125 thousandths thick. Because a lot of people say, put your focal point in the middle, and that sounds, it makes sense intuitively based on a really simple diagram of the focal point and the cone shape of the laser beam, but that's not really how it works. For a 1/4 inch like this, you would say, well, maybe then at 1/8 of an inch is where the focal point was. When I did all my tests, as I said, I took all of the materials that I had previously run that I knew I could cut through in one pass, and I tried a focal depth, and now I can't go by the depth of cut now because they're all cutting through. So now I have to use speed as my judge. So then I went back to this pattern where I just simply cut at different speeds, and sometimes I don't waste my time trying to cut at these really low speeds because they start fires. I have a good example of what that looks like right here. If you run generally 5 or 10 inches per minute, which is 127 or 254 millimeters per minute, those are bad news for wood products generally, at least with this laser power and this cone shape. You're feeding oxygen in there by pumping air with the air assist, and the fringe parts of the beam don't have enough energy to instantly vaporize it, but they do have enough energy just to sit there and smoke it. And you can see here too, I started this one on fire. So generally speaking, you need to keep the speed up at least to 15 inches per minute or 381 millimeters per minute to get clean results. So what I found generally is that I want to stay above 15, and then if I can cut multiple passes at 25 or 30, say 15 or 30, that's about the same execution time, but maybe 2 passes at 30 will give me cleaner results. So that's kind of how I tried a few different things that way. So anyway, I was cutting single passes on all these thin materials, running and then basically writing down what's the fastest I could cut through that material, and I did that at 0, and then I did it at the midpoint, and then I did it at that same minus 200 thousandths that I had found for deep wood cutting worked the best. And what I found was that anything under about 1/4 inch gave me the best results with the focal point right on the surface, which was interesting, but I guess not too surprising. So I basically have 2 optimum set points for cutting then on thin materials that are one pass, that are less than 1/4 inch. Then I just set my focal point like I've always been doing for years, right at the surface. But then if it's multiple pass where the first, second, or even third maybe pass won't go through, I'm gonna first use my touch plate to get my reference point, and then I'm gonna lower it another 200 thousandths and use that for my Z0. That significantly increased, especially on the thick materials. I had several materials. There's 3 different things I could not cut through. I could not get through this cherry at all with even 3 passes originally, and then when I used the new 200,000 sound, I could cut through cleanly. Even almost got through at 20, but I cut through cleanly at 15. I could cut through this thick Luania at 25 inches per minute. And one of the other things that I could not cut at all was the 1/2 inch Baltic birch. The 2 things that seem to be the hardest things for the laser to cut through are Baltic birch and MDF. MDF and Baltic birch, they end up having a lot of glue and they're highly processed, so it's a much harder, denser material than solid wood, believe it or not. And so they're harder to cut through, but once I got the depth right, you can see I could get up to 20 inches per minute cut 2 passes, which is pretty cool. So anyway, let's go talk about the beam itself and why this doesn't follow kind of an intuitive reasoning about where the cutting depth should be set. So let's take a look at the beam and where the energy is in this. If you take a CO2 laser beam, they're nice and round, they're very uniform, X versus Y. The laser tube in those generates a very symmetrical beam. The density across that beam significantly varies, just like an LED diode laser. So if you look at the beam width, the energy density still is very exponential, where it's in the center of the beam has a lot more power density than out in the fringes. And so this is why we always say you have to try out the specific material, the speed, and the power setting anytime you want to do engraving and you really want to know what the exact burn mark is, because if you run really fast on a really hard material, you're only going to get a little dot like that because there's only enough power density to actually burn it at that speed, in this little part of the beam. But if you run slower or on something really soft or run more power, now some of these lower density parts can also cause a burn, and so your beam can start getting bigger and bigger. Well, the LED beams are even more complicated because they're not a nice symmetrical source. Each LED actually leaves a beam that's shaped like about 1:4 aspect ratio of width, and then inside that the power density is even weirder because there's another axis in here where the really high power in here is concentrated right in the center, and the width of it actually goes this way, perpendicular to what the big part you see. Like if you take your laser and Z it way up, you're going to see this thing here, but it doesn't cut. This stuff isn't used at all really for cutting. There's not enough power there. You can see it visibly, but when you focus that down and cut, you actually get an image that goes the exact opposite way. That's a single diode. Now this XT8 has 4 diodes in a row on the 4 diode mode, and then when you flip the switch, it adds 4 more diodes in, but those images are pretty much stacked right on top of that. So now we've got 8 independent beams. They're clustered together as close as the manufacturer can try to make them, but they're distinct, and then each one of them has their own little high density point right in the middle. So how the energy density across that beam as it comes into the lens to start with is pretty complicated. It's really a series of, or a bunch, 8 different spots that have an asymmetrical power density. So we don't really know exactly what it looks like when you focus it down. So I'm just going to talk about this a little bit as a simpler case of just the CO2 one to start with. So you've got the CO2 beam, and let's just say it's a perfectly collimated, so it's doesn't have any divergence, but true laser beams all diverge a little bit anyway. But like I just said, the power density looks like this. It's very dense in the middle and it's weaker out in the outsides. Now, as this goes through the laser or through the lens, the outside parts they're turned by more of an angle, and the object is to try to get all the different parts of this beam to converge on one spot to give you the smallest dot size. Now, Russ does a really good job in the video, and I've got the link down below in the description section to go watch some of his stuff. He's got hundreds of videos, lots of them on lenses. He's played with lenses a lot. It's really cool, but there isn't one focus point in all these different, like if you look at where the outside two converge versus where these other ones converge, they're in different spots in here. There isn't actually one convergence spot. So when you're doing your focus test, you have different contributions from different pieces of this. So that's one thing. So the other thing to remember here is that some of the energy right in the middle here, if it comes in straight on that lens, it comes straight out of that lens. And if it's coming from the edge and coming in at an angle like this, it comes out over here. So only some of the fringe power is what you really see. So when you lift up your laser on your CNC, you see that beam get bigger and bigger, and you go, okay, you can actually calculate what that cone shape is, because if you have it here and it's so much width, and then you raise it up here and it's wider, you can figure out how many degrees that is. But what you're kind of tricking yourself, and this is how I fooled myself, is all you're really doing is telling yourself how wide the outermost portion that you can see on your spoil board is. But that's not really doing any cutting or anything, unless you hold it there for a long, long time and start a fire or something. But what really does the cutting is all this high density stuff right in the middle, and that diverges a lot less. So, and this is what always fooled me, is I would see this and I'd go, okay, if I had my board here, for example, I get a really small dot here and I see a really wide exit wound, if you will, of the wood on the bottom, and I would always think, well, I'm going to get the best cutting if I actually center this board on each side, because now I don't have this big wide part. I've got a smaller wide part on the top and the bottom, and I'll get overall the best burn all the way through there. But that's not really how it works, because this beam is so complicated inside, and we really don't know where the most energy is for the longest distance, and that's really what matters for cutting deep. We can't really tell from just looking at the shape of the beam. We really have to characterize it, like I showed. So the somewhere in here is really the energy that matters for cutting, and that's why I just did a test where I kept moving it down and find out where the sweet spot is. Where do I get the most energy for the longest amount of distance through that deep wood in one pass? And what's and then I want to run it at a fast enough speed as well. So, because what you're really trying to do is the power density in that centerpiece, that vaporizes whatever it hits. So the wood burns and vaporizes so fast that it doesn't even get the chance to start the adjacent wood on fire. And that's really, with laser cutting, that's what you want. You have to have, there's kind of a threshold between just turning it dark or melting it or turning it into charcoal versus just instantly vaporizing it. And that's what we're looking for here. If we go too slow, then these fringe things now before those fringes had enough energy to warm it up a little bit, but they didn't discolor it, they didn't burn it, they didn't cut. So if we start slowing down too much, all of this stuff on the edge here, and even if you're down farther, this stuff up here, that'll start to actually discolor the wood, and as you go faster and faster, it can start fires. And this is what causes the problem on really thick wood. You go, well, I can almost cut through at 15 inches per minute, so if I run it at 10 or 5, I'll cut through for sure. It's like, no, actually you just start a big fire, because now all of this stuff kicks in. You've got oxygen blowing in there. I started fires in quite a few different things in testing anytime I went down to 10 or 5 inches per minute. So I kind of, for this laser and its characteristics, 15 inches per minute is as slow as I will go before I just say, well, I'm going to cut that in 2 passes at 20 or 25 instead of, lower speeds, or maybe 3 passes, because then I'm just basically, this long skinny part going down the middle has the ability to keep going infinitely straight. Now the energy does get weaker and weaker as you get deeper, so after about 3 cuts, for me, if I can't cut it in 3 passes, to me it's not very capable. Or it's not a reasonable thing to do with the laser. I know a lot of people on the internet, they'll run 10 or 20 passes and say, oh, it cuts it. But to me, that's like, it's kind of like trying to cut through wood with, a piece of plywood square, cutting it out with a jackknife by dragging it back and forth a million times. It's just not the right tool for the job at that point. So I always stop at 3 passes, but it will, and on the second and third pass, the incremental cutting depth that you get, it's diminishing with every pass, and that's why I say it's like you're not really doing much after the 3rd pass anyway. So, but that's my attempt at explaining why going too slow is bad and why it actually cuts deeper than it seems like it should based on this, and it's not in the same place. The optimum depth isn't the same place as it seems like it should be. So, and then it's, like I said, it's even more complicated for a diode laser. There's just no way you can figure out where it's going to be. You have to actually just characterize it like I showed with the different depths, and actually measuring, looking at the depth and seeing which one gives you the deepest cut and also the clean cut that you're looking for. So let's take a look at my final results table. Most of these items here, in the up in the top here where it's only 1 pass, those improvements were just due to the laser. The newer laser did have a little bit better driver, and I'm not sure and the nozzle was a little bit different height, but across the board with the same conditions, it generally did slightly better, about 5 to 10 inches per minute maybe. But when you get down here into the 2 and 3 passes on these really thick materials, this is where having that focal height change really kicked in. I was not able to cut through 1/2 inch MDF, that 0.7 inch thick piece of cherry, or the 13 ply plywood at all. And once I ran that with all passes at the 5mm lower height of focal height, I could cut through nicely at 20, 15, and 20. So those are respectable speeds in only 3 passes for that kind of material. So, and then on 2 passes on some of these items, it literally doubled my speed to get through. Even though I could get through them previously, I could cut through twice as fast now. So that's a significant improvement just from changing the focal height. All other conditions were the same. So this is kind of a summary. So after characterization on this laser, these are kind of the general rules I have for it now based on that characterization. Now, if you have a completely different laser, you're going to have to do the characterization to find out if,
what these numbers will be different for sure, and maybe even the focal height for thin materials versus thick will be the same. I don't know. It just kind of depends again on where is the energy density in that beam. But for me on this laser, anything less than 1/4 inch, I found I get the best, fastest cutting, cleanest cutting with the focal point sitting right on the top surface of the material. So same focal point as I would use for engraving, for example. But if it's anything past 1/4 inch thick, then I'm going to drop it down another 200 thousandths or 5 millimeter below that point that's up here. And this applies the same to all passes. And also what I had mentioned is pretty much for any organic materials, wood, leather, stuff like that, is I don't want to be cutting below about 15 inches per minute with this laser, because it just starts to burn. Those fringes of the cone start burning too much, and it's just hanging around in that spot too long. So I always dial my speed up to stay at 15 or higher on that. And then I also did some characterization on the airflow. Everybody else asks about that. You definitely always want to have airflow with the laser. At least I never go below 5 liters per minute, and the reason is the one main thing that you always want air for is to keep that lens clean. You got to have positive air pressure coming out of that nozzle. Otherwise, you're going to end up with smoke and debris flying back up in there and getting your lenses dirty. And as soon as your lens gets dirty, now that light going through there can heat up the debris on your lens, and it can get very hot actually and destroy your lens. So it also affects your cutting performance obviously, but you really want to protect your lens. So always at least run with 5 liters a minute. You generally want to run with a low value for etching or doing pictures, because otherwise it can stain and do some things that kind of make it harder to clean up later. But if you're cutting, what I found is 10 to 15 liters per minute is a good range. Pumping in too much air doesn't really help. It can even cool down the cut and slow it down to some degree. So 10 to 15 liters per minute is generally a good spot to be for cutting, no matter how deep it is, how thick the material is, how thin it is. And then, like I said, around 5 liters per minute maybe is your minimum that you'd ever want to use. So that's it. It's a pretty simple set of tests to do to figure out where your laser cuts the best. And as I mentioned, it's probably going to be different on every different laser. Even the same model might have slightly different characteristics. The other thing is, take a look at the videos from Russ. I'm going to put a link down in the comment section. Like I said, he's got a lot of really interesting videos and good ideas on how to characterize things, and a lot of microscope shots of what's going on inside the cut or inside the burn. So it's pretty interesting. So give him a check out too. And if you have any questions at all or comments, throw them down in the comment section. I always respond and appreciate any feedback or questions people have. So thank you.